Okay, so let's continue. So we finished with the L1 regularization. And as I mentioned, we need to do these regularization procedures because, not always we can easily find this minimization point. Not always we can find this minimization point because, we're not always minimizing our loss function for our machine learning model in this nice perfect ball. Okay, so, and how the L1 regularization is looking like? L1, as I mentioned to you, is just a sum of the absolute values. And if we draw it in 2D, instead of circles, we're going to get a nice squares. And why kind of like, it might be a little bit more technically challenging to calculate L1 regularization kind of on the computer, because as I mentioned to you that, if we apply some numerical algorithm, the advantage is that it scales linearly with the position, but the disadvantage is that mathematically speaking, it's a discontinuous function. And when we're going to do this numerical search for the optimum between our minimum loss from the data and the minimum loss from the regularization, we might end up in some points where the derivatives are not defined, and our algorithm needs to be able to handle that. But again, this problem is solved by us within the packages which we are going to consider. It's already done. Okay, the question in the chat is, what is the difference between regularization and gradient descent? It looks like the same without the notation. Okay, so the gradient descent is a way to find the minimum value, because linear model and a couple of other models are allowing you to find the analytical solution where this minimum point is in some cases. And the gradient descent is the way to do it numerically. And we're going to talk about the gradient descent just now. Okay. So regularization for the feature selection, yes, so we can construct a lot of features and add to the feature maps. Afterwards, we can use L1 regularization to select the subset of features which give us non-zero coefficient. Okay, so that's what I mentioned to you in this bit, kind of like what we want. Sometimes we get too much data. For example, what we're going to see in the example of the very, very simple data set, which is, we need to learn to predict the prices for the houses with some standard housing pricing data set. We're going to see that for some features, they are irrelevant. And so kind of we want to apply some methods so that we can say that, okay, so out of all, 100 input values of the input vector, we're not interested in all 100. They're not relevant for our machine learning algorithm. Maybe for some other research purposes, they are interesting. But for what we wanted to predict, it's irrelevant parameter. And we want just to throw off this parameter, because the less parameters we have, the quicker the model is, or the quicker the training is, the quicker, the easier is to explain why the model is making decisions as it's making decisions, why it's saying that, that the price of this particular house should be this amount of dollars or that amount of dollars, and things like this. Or kind of like why the thickness of the ice sheet should be this or that, as the function of some parameters. So when using this L1 regularization, we can get kind of the importance of these betas and find which are betas are important, which are not important, and we can throw away unimportant one for this particular problem. Okay, so that's, and after doing that, we can throw away unnecessary features and apply the retraining of the model and compare the performances. Okay, so now I've been talking for quite a long time, so that we need to minimize the loss. but I never told you how we can go into it. And again, because we're dealing with, we want that our the machine learning algorithm is equipped with some kind of tools which can minimize the loss and find the optimal betas, how we can do it. And linear regression, or the beauty of the linear regression and several other models, so that we can do it in two ways. So we can really write a closed form solution for the minimization of the mean square loss, and we can kind of for the more general cases, we can find what is the numerical ways to minimize the loss. And that the way which we are going to describe was already asked by somebody in the chat, and that would be a gradient descent. And although in this case the analytical solution could be obtained for the wider families of model, gradient descent and the based on the gradient descent approaches or kind of some other approaches are much more efficient or much more useful, because the closed form solutions just do not exist. Okay. So in order to obtain the vectorized or kind of the analytical solution for the linear regression, we need to do an epsilon of math, which is very useful, I think, exercise, because it's very good kind of to understand, kind of on which grounds one can do certain calculations, because they could be very useful for some other algorithms as well. Okay, so we have let's put all our inputs with application of our f for linear regression into the vector, f of x1, f of x2, blah, 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 f of xn. It's a vector with n components. Yes, and of course, each f is just beta transposed on each vector x1 and so on, meaning that each of them is just a sum, sum over j. And you remember that the j is the internal index, and the I, which is here, is 1, is the external index. So I1 is the item in the data set, and the j is the kind of the internal number of features of the vector. So, and this vector could be very nicely represented because it looks like a matrix multiplication, but you just need to swap x, ij, and the beta j. And so it could be written like this, as the matrix of all input vectors. So, all your rows are the input vectors, and it's multiplied by the beta. So essentially, all of the linear regression is doing, it's just doing the matrix of inputs multiplied by the beta from the what we might think is the kind of wrong side, but in fact it's looking like this. And what we need to do, yes, we need to that when the vector of y's of the known outputs is roughly the same as this product of the x on b. Okay. So now how we can vectorize mean squared error? So mean squared error, because this is our kind of L2 norm, or kind of the standard Euclidean norm squared, so or x minus y squared, sum over the all components. This could be written like this, capital Y minus x beta squared, where this squared norm means just, Euclidean or standard, the Pythagorean norm squared. And now what we want as a closed form solution, we need to minimize this function. When this function is, how we can find the minimum of the function. To find the minimum of the function, what do we need to do? We need to find the derivative. Yes, kind of like when we have a one-dimensional function, how we can find where the function have an extrema. So where it have a minimum or maximum, we need to find the derivatives and find the zeros. And in the points where the zeros are, we need to analyze, is it maximum or minimum, using the second derivative. Yeah, but here we don't need to go to the second derivative, because we know that this function, which we're minimizing, it's only have a minimum. So what do we need to do now? We need to analytically calculate the zero from this guy and find what the beta should be. And you can convince yourself that the derivative by all the betas, or what is called the gradient, yes, because if you in multiple directions, we need to construct a vector from the derivative along each axis. Yes, I assume that everybody have some familiarity with that. Yes. There is nothing happening in the chat, but I assume that the people should know how to find the minimum of the function, if this function of one variable or two variables, or n variables for that matter. So we just need to find a derivative with respect to every beta, so beta 1, beta 2, beta 3, and so on, and construct a vector. So and one can show that derivative along each of those will be written like this, which is a linear function, which is very good. And so I think somebody is raising the hand. I think it's useless to raise the hand. Please type in the chat in the Slack. So, and we get a very simple equation, which we need to solve. So by setting that this vector of all derivatives should be 0, we will have that this guy have to be 0, or if we just throw this side, this term on this side, we get that this guy have to be 0. So in order to find the optimal betas or ideal betas, at least from this perspective, we just need to invert this matrix. Yeah, so, and we can write that this is the optimal betas. So and in principle, you know, kind of the problem of linear regression seems to be solved. And why we never do it, or kind of why we do it in very specific cases, there are multiple reasons, also kind of like related to the numerical implementation of law. Yeah. These closed form solutions are unique only if this matrix, X transposed on X, is invertible. But that's, those of you who have done any numerical analysis know that, you know, if you take some arbitrary metrics, it's not necessary to be invertible. And otherwise, you know, you can have multiple solutions, or you can have, you know, some problems. For example, you know, if you have, you know, your XTX is looking like this, your solution will look like this. So you have infinitely many solutions. So that's one problem. Second, purely computational. The calculation of this thing could be, this inverse could be challenging because computing of the inverse is scaling as the third power of the size of your matrix. So if we have 10,000 features, the time which it takes will be proportional to 10 to the 12 of whatever units of time we take. And it doesn't really matter, is it seconds or years? It's a huge number. Yeah. So, and even storing metrics like that might require quite a lot of memory. And there are even more difficult numerical issues which are related, so that, you know, the matrices, there are matrices which are called ill conditioning, so which are barely invertible. So it means that it's a very difficult task, and you need to apply tricks in order to invert such metrics numerically. Okay. So, and as I mentioned again, kind of like, and that is only working for the linear models. So that's why, you know, it's very nice. It's help if you want to do some analytic research, kind of like functional research within the machine learning field, and you want to prove some bounds. The fact that you can write analytic expression is very useful, because usually kind of the axiomatic proofs in the machine learning, people use certain assumptions on your data. For example, they use that your data is taken from the normal Gaussian distribution, and that's something just called IID, or kind of like there are some extra requirements which are making sure that, you know, you can say something about this inverse very nice. But in real life, it's not necessarily the case. And that's why we need to go for the numerical finding of this beta, or numerical minimization of the loss function. And how we can do it? Again, we can do it using the properties of this gradient function, or taking a minima. And in order to speak about, and this approach is called gradient descent. And based on this approach, many other approaches are developed, because again, the vanilla gradient descent, or gradient descent, which I'm going to talk to you now, will be very challenging, for example, for the modern neural networks and things like that. But this is the basics. And based on this, you know, people develop approaches. What is the fundamental idea behind the numerical approach to the gradient descent? The idea is very simple, is that when we're taking a vector of gradient from the function, yeah? So where this vector is pointing out, this vector in the point on the surface is pointing out into direction of the most rapid growth of the function. So if you have a multidimensional function, you take a gradient, meaning that you take a derivative with respect to each parameter of that or each variable of that function, and you evaluate this function in some point, and this gradient or bunch of derivatives will point out into the direction of the highest growth or the quickest growth of the function. But that's not what we want. What we want to go to the minimum point. So it means that we need to move with the gradient, but in opposite direction. Yeah. So, and that's automatically telling you how we should apply automatically this gradient descent. So we need to choose some initial values of this vector beta, and how to choose it is a separate, what is called a hyperparameter, or a separate discussion. So you can choose it randomly. You can choose it randomly from the uniform distribution. You can choose it randomly from the Gaussian distribution. You can apply some other tricks, and as a function of the problems, people decide how to do it. And afterwards, what you do, so you calculate a gradient in that point, kind of for these values of betas, and you update your values of betas by moving away kind of in the opposite direction to the maximum growth with some velocity alpha, which is called a learning rate. And how to choose that is also an extra hyperparameter or extra parameter which you need to tweak. And why it's going to be kind of visible in the couple of slides. Okay. And how it looks like and why the gradient descent is working is sort of how you do it. You choose some random values, and you see kind of this is already better looking like a landscape of the loss function as we have it. Kind of like in some more realistic scenarios, that is already what we're talking about. So that it's clear that if you start from this hill, you can go down this valley, and if you do these small jumps, you will naturally end up here. And it's obvious on this graph that in principle you want to end up in this kind of minima, at least for this function. And the question is how to do it and how to obtain the best way in getting into that. So you choose some initial value of beta, and you begin to, and that's why we need regularization. You need to move until you converge. What does it mean converge? Until the change between your loss functions before and after your step doesn't change too much. And what does it mean too much? It depends on you. You are telling to the algorithm what is your precision, what is your how fine you want it to be. Yeah. So kind of like you choose another value of beta and you get here. And essentially the strategy is that you choose randomly multiple values of beta, and you see where you converge in most of the time, so where you get the minimum loss. Okay, so for our gradient descent for the linear function, we have a wonderful landscape which doesn't have a multiple minima. It's having kind of at least the pure MSE loss have a single minima, and there is no local minima. It's called a global minima, and the walk is happening relatively easy. So when one can, for example, apply some very simple strategy, you initialize with 0, and afterwards and for bit 0 as a function of the landscape, you can be somewhere here in this graph. Yeah. So and afterwards, you just choose. You need to choose some alpha and apply this iterative step until you reach minima, until the difference between beta t plus 1 and beta t is small enough so that you're saying that, okay, I'm happy with where I am. And the logic is, of course, yes, kind of like in 1D case, what the derivative is showing you, derivative is the tangent to your curve, and negative derivative, the positive value will show you the direction up, negative in the direction of growth of the function, and with minus will show to the direction of the decrease of the function, and so that you can do this iterative step, and afterwards you will stuck here. And the important thing is, and I think it will be on one of the slides, that we need to play with this alpha in order to achieve the best results. Yes, kind of we repeat it until convergence. And what the convergence means, it means that the difference between these two vectors is smaller than some parameter epsilon, which you need to define, which you as a machine learning kind of person who is designing machine learning algorithm or choosing the parameters of the machine learning algorithm, you need to take and say in advance. You can say that, okay, until epsilon is 10 to the minus 6, or until epsilon is 10 to the minus 12, or until epsilon is 10 to the minus 30. So it's up to you, but what you need to know, the smaller the epsilon is, the longer it will take to reach a precise conversion. So it's a trade-off between the time you need to take to optimize against time you have or computational resources you have. Okay, so kind of learning rate is another parameter, as I mentioned to you, which one need to choose. And it's also a little bit of art or kind of understanding how to choose it. If you choose the learning rate too small, you will be on the right path, but you will move too slow because your jumps between the successive betas will be just too close to each other, and it takes too long. If you choose the learning rate too large, you're just going to jump in between the kind of your jumps will be too large, and you see that if you could even end up with a situation when your kind of the loss is increasing, which is also not a good scenario. So, and the strategies for choosing the learning rate is a separate set of strategies, and there are kind of like typically people start with a larger learning rate, and afterwards kind of there is a built-in tools which allows you to decrease the learning rate kind of as you do the minimization strategy. But you can have also a reasonable learning rate to try to play with. So alpha is a hyperparameter for the gradient descent, and we need to choose. So rule of thumb is loss decreases too slowly, alpha is too small. Loss increases, alpha is too large, and typically one can just play the game of trying. You just create a set of alphas and you train your algorithm for all this set of alphas, and suddenly you see what performs better, what converges better, and so on and so forth. But the idea is, like, you see now you're getting more and more parameters to play with, and that's the difficulty. So that's what one need to try to address, so that now we need not only to choose the parameters of the model, the parameters of regularization, but also parameters of the gradient descent. So when you get more and more parameters you need to choose, and that's becoming more and more a little bit of art, and there are too many rules of thumb. But okay, what can we do? Okay, so we can compare the strategy for the linear regression for the closed form solution. There is no extra hyperparameter. So it's slow if n and d are large. So if we have too much data, closed form solution is not very optimal. Yes, it takes too much time. So with the gradient descent for linear regression, we still need to choose. We need to choose this hyperparameter alpha, but at least it scales okay to the large n and d. But there are also other problems which I mentioned with the closed form solution, that you can have mathematical difficulties with inversion of the matrices, and that might be the bigger problem. And the beauty of the gradient descent is that here we don't care that our loss function is in the linear regression, and we can use it to train any other model using the gradient descent or some derivatives of the gradient descent, while closed form solutions are only possible for the very narrow class of models. And that is why kind of closed form solutions are elegant, as I mentioned, but they are not very practical. Okay, so we can also analyze how to minimize the loss using the linear regression with the regularization. So in this case, it's L2. We can find the analytical gradient. We can play the same game. We will get, gradient is equal to 0. We will get expression, and we can again find analytical solution. And this guy is much better behaved because we have this extra term to invert, and it's proportional to identity matrix, and it's always defined. So kind of this matrix, not the XTX, but XTX plus n lambda I, or n lambda identity, is much more invertible. It's usually that's usually how you sort out the problem of non-invertibility of some metrics. You add the extra term which is proportional to identity with a small parameter, and you kind of numerically invert it like this. Okay, so for the gradient descent, we get a slightly different expression. And essentially, gradient descent do not care as an algorithm that the fact that now we have not just ordinary linear regression, or we have our linear regression with the extra term. Okay, so that was, if I'm not mistaken, that would be it. What I wanted to tell you about the linear models. Let me see. Okay, there is nothing in the chat. So in supervised learning scenario, yes, kind of, and it's in general, it's irrelevant of the linear models. So we have some data which is coming in couples. So we have an input data X, which could be a vector, which could be, kind of multidimensional vector, because which could be an image. An image is a multidimensional vector, or kind of a matrix, multidimensional matrix, more than kind of the two dimensions. For example, the colored image. Yi is the real number usually. So what we do, we choose the model for which we're minimizing the loss function such that the yi's are approximately approximated by our function of beta. And in case of linear function, this is a linear function, but in case of any other approaches, kind of like neural networks, this will encode the neural network for your support vector machine, or random forest, or whatever. Okay, and we'll use afterwards this model to predict new data. So, yes, regression, Y's are linear values. For classification, for the next class of problems, which we are going now to talk about a little bit, is Y's are discrete values. And as I told you, in the simplest case, it's just the two values. And this is called a binary classification. It's a yes, no answer, or class 0, class 1. In the more classes, it could be, any number of discrete number of classes. It's just, it could be 1 to k for the k classes. Okay, but the game is the same. So we need to choose some loss function, but now we need to think a little bit more carefully about what the loss function is. And we need to choose the parameters of the model such that it's minimizing loss function, and we get in the model. And as I mentioned to you, the easiest possible model is for classification is the easiest possible case for the classification is the binary classification when you have only two classes. Or you can think of it's a problem where you have some input data and your answers could be yes or no. So in this particular example, it's is kind of the, if there is an ocular tumor, is it that, or is it okay? Yes, is it malignant, or is it benign? Okay. So how the solution for the kind of thing, if we want to apply again, we've learned with you only about linear functions. And if we want to apply the linear functions for the binary classification, how the solution will look like. For example, in this example, if we have an input 2 points, or kind of the two-dimensional data, x1, x2, linear functions can create to us what is called the decision boundary, or kind of so everything who is on the blue background is classified as the blue dot, and everybody who is on the red background is classified as the red dot. And this is kind of like, the task of the classification is to draw this line, which is separating yes answers from no answers, or class 1 from the class 0, or if you have, several classes, as we are going to see, you have, several boundaries. So yi's, or labels for the binary classification, is 0 and 1. So what we want to predict when yi is roughly 1 for some condition satisfied, or in this condition, if we want to use linear models, could be very simple because we have this beta on x is a number, so we can design our algorithm in such a way so that when this quantity beta on x is positive, it's a class 1. When the beta on x is negative, and we need to choose such betas, it will be a class 0. So, and the question is, what kind of loss function? Because as you see, everything is revolving around the proper choices of the loss function. What kind of loss function can we choose for that purpose? And the natural thing is, again, we've seen that the loss functions, which are based on the distances, works relatively well. So let's think about it. So let's take all the points which are misclassified, because obviously, that was our red points which end up on the blue background. So they're misclassified by our classifier. And let's calculate all the distances of the all misclassified points. And also there is one, in this example, there is one blue point is here. So we calculate the distances to the border and sum it up. Yes, so we calculate the distances from all misclassifying points. So if our loss is minimized to 0, it means that there is no misclassified points. Then we have a 100% accuracy. And the variant of this loss is used in the objects which are called support vector machines, which is the linear models with a certain very interesting feature maps. But we're not going to talk about them here, but they're quite actively used, for example, in quantum machine learning. But maybe this kind of approach is not always perfect. And the question is, what other approaches one can try doing? Okay, so in order to understand this kind of what is the typical approaches which are taken in this part, we need to kind of step a little bit aside and talk about what is called probabilistic viewpoint on the machine learning. And unfortunately, yes, my lecture is coming before the lecture on the probability and statistics, because if it was afterwards, I think you would have been a little bit more comfortable with what I'm going to say. But okay, let's assume that we all have a little bit of intuitive understanding of the probability and some basic ideas of statistics. And let's try to use the probabilistic viewpoint on the learning process. Okay, so given some input vector xi, we suppose that yi, so that the answer is drawn from some distribution, is drawn IID. So what the IID is standing for? It's standing for what the IID is standing for. Who knows the statistics? What's happening in the chat? Okay, IID is standing for independent and identically distributed random variables. But what does it on intuitive sense means? It means that, the values of yi's are independent from each other. It doesn't matter, am I taking yi of this value and afterwards that value, or in reverse. So they are independent from each other, so that we can apply all sorts of very simple rules from the probability theory. And so what is the basic idea of the probabilistic view on the machine learning? Kind of what we want to say, that what we wanted to estimate is the probability distribution such that, or kind of the model family of the probability distribution such that, so when we input values of x and some tuned parameters beta, we're going to get the distribution of the y's such that distribution of the y's will be as close as possible to those y's which we have from our data set. So, and in this case, y is treated as a random variable, not a given vector. Okay, so and typically this is written as p beta, so probability distribution, which is defined by this set of parameters beta, such that current random value is equal to of y is equal to y, given the input value of x. Okay, so, and if it sounds a little bit esoteric or a little bit exotic, don't worry, because now we're just going to have a very nice example related to linear models, where it will be clearly seen that there is no difference to our normal linear models. It's really a different viewpoint, which is very useful viewpoint. As we see, it will be very useful for our classification problems, where we want to estimate, where we want to have a nice loss function to work with. Okay, so there is nothing in the chat. Let's continue. Okay, so compared to the loss function in the linear models which we've just seen, so what we were trying to approximate when the kind of each component of the vectors of the outputs is close as possible to this functional output, so to say, of the f of linear function. And now that it's coming from the kind of what is the probability to get the yi given input xi with the parameters beta. And the difference is this f of beta is just providing one point, which should be close to yi, and this is providing you kind of a probability distribution. So it's providing you many y's, but these many y's should be distributed somewhere nicely around your real y value. Okay? And maximum likelihood estimation combine the loss function and the model family design decisions. Okay? So, and take into account that all our inputs are independent, and that's why that IID hypothesis or IID requirements were important, which not always works, but that's an assumption. So the loss function could be just seen as this kind of conditional probability distribution, and because all the points are independent, it will be a product of each kind of what is the probability that for the input x1 where I'm getting y1, for the input x2 I'm getting y2, and so on, because x1, y1, x2, y2 are independent from each other, so the probability of these events happening together is just a product of the probabilities. And it sounds not too bad from the point of view of optimization, but the problem is, just imagine that probability is a number between 0 and 1. It could be a very small number, and when you multiply a lot of very small numbers, you can get even smaller number. So this is a problem. So, and very often what's happening, you go from the likelihood, so you want to get rid of the product. You go to the sum. And to go from the product to the sum, you can, by the operation, which is called logarithm, yes? Because the logarithm of the product is the sum of the logarithms, yes? And this is called negative log likelihood. So we just take a log of it, and we take it negative because log for these numbers which are smaller than 1 are negative, so that it's a positive quantity, and we can minimize it. So that's why we add minus. Okay, so, and if it sounds a little bit exotic, let's try to go to the kind of like, first of all, the intuition is that, we choose this beta such that, this is a high likelihood, which correspond to the low negative log likelihood. And this is low likelihood, yes, because if we're saying that everybody who is here is one class, everybody who here is other class, it's obviously we're doing something wrong. Well, here we're doing something right. Okay, so, and let's now try to build the bridges to the linear regression. So now let's assume that our conditional density or our probability distribution, yes, so kind of a conditional probability of for the given xi given yi is looking like this. So it's looking like a normal distribution where we take the exponential of the difference between the beta x, between the prediction of the linear model minus yi. So it's for this couple of parameters is looking like this, and this is exactly what it is. It is a normal or Gaussian distribution with the mean mu and various variance sigma. So now if we take log likelihood, it will be the product of the terms. But if we take log of it, we're going to get a bunch of constant terms, which we can ignore. We can throw away because they just, but what we get here just a standard minimum square error, yeah, up to the factor 1 over n. So, and this is kind of, by choosing such probability distribution for our model, we show how it's related to we're just getting a linear model. And now when we're minimizing this quantity, we're just minimizing a loss function of the linear model. So, and that's how essentially there is, from the point of the kind of axiomatic machine learning, or kind of, or it's just a statistical approach, a probabilistic approach to the machine learning. It's solving the same problem. And it's obviously obtaining the same solution. Yes, because now loss minimization for maximum likelihood is, again, we just go for the all possible betas such that we're minimizing this loss. Yeah. And our negativity is related to the fact that, yes, it's negative so that we are minimizing it and not maximizing. Okay. So now the question with this linear regression, what about the model family? Yes, kind of like we know that we have, this is our this is our linear function, which corresponds to the maximizing log likelihood, or just the likelihood, maximizing just the likelihood. So, and here it's obviously happening, the question is for which y's we're getting the maximum. Yes, kind of, and which y is when the y is equal to the beta transposed on x. So when we get a linear regression. So that is a very simple connection. And it's essentially, maybe it's sounds a little bit strange, but it's exactly the same. It's just a different views on the one and the same approach. But this probabilistic kind of view or kind of statistical view will give us some tools to solve kind of a wider class problems. And that's why, it's very interesting and kind of it's used in the field. Yes, kind of maximum likelihood view of machine learning. So you have a two design decision. So probability of data given the parameters beta, and kind of optimizer, how to optimize negative log likelihood. And we optimize it using the gradient descent. Corresponding loss minimization view, again, is a model family is when we're maximizing, we're going for the all possible answers, and we're maximizing our probability distribution. And in that case, we're recovering the model, and the loss function is negative log likelihood. Again, so this is essentially the same. It's a very powerful framework for the designing cutting-edge machine learning algorithms, and so on and so forth. And as I mentioned to you, kind of all of this is based on the idea that these, different pairs of the x and y's are independent from each other. But in fact, in the real world, sometimes it's not the case. But still, these probabilistic approaches, which involve these conditional probabilities, they allow you to tackle this problem, and that's why it's very actively used. Okay, so how can we apply these games to the classification? And we can apply it in the following way. So we can say that, we have our probability distribution, and we can say that that for class 0, it will be proportional to the e to the minus beta x over 2, and for class 1, it will be e to the beta x over 2. Yeah, and now if we want just, because if we just, this is just a proportionality, if we just, want to calculate what is the probability of 1, we just need to take this probability and divide by the sum of probabilities, so because probability is supposed to sum up to 1, and we get a function like this, which is a very interesting function. It has a special name. It's called the sigmoid function, and it it will be on the next slide. But it's the interesting property of this sigmoid function that for probability 1, kind of the probability that the y is equal to 1 is a sigmoid, but the probability that it's just pure mathematically, you can show that it's 1 minus sigma, as it's supposed to be. But it's very interesting, so that both probabilities are related to explicitly to the sigmoid function. And the sigmoid function is looking like this. And this is explicitly and this is kind of for the sum value of beta in one case, and it's explicitly give you this kind of boundary decision. So if you are above 1/2, you're in one class. If you're below 1/2, you're in the different class. And your task of choosing betas is such so that you choose it so that it's better fit the data. Okay.
There is a question on Slack.
Do we always use both? Do we always use both methods, analytical and numerical and statistical, or do we choose one? If so, what is the methodology to choose the method? Okay, so first of all, you always choose numerical method by default because it's the easiest and the most straightforward one. And if it doesn't work, you start thinking. Essentially, that's a rule of thumb, because kind of like if you throw simple method, you just start slowly and you see what's working. But if some kind of applying some linear regression with a couple of features in the feature map works well, and it satisfies all the properties what you need, you can first interpret the results very easily, and you can just keep going, because in the moment when you need to apply some extra methods and see kind of like have an argument about the model family decision or kind of model families and try this model, that model, in that case it could be really kind of time-wise and compute-wise costly, and it depends like which resources do I have access to. But ideally, and why we need all this regularization, you want to apply as simple method as is possible, but not too simple. And that's a story. And choosing between the statistical methods and numerical methods is also depending on what you wanted to do. For example, sometimes you get a situation when you don't have enough data. And in that case, what you can do, that's where the power of the statistical methods are coming in. So you can try to estimate the distribution from where your data is coming from, and you can sample more data using the obtained distribution. Of course, it has its own caveats, but it's a complementary methods, and you apply them as a function of what's going on. Okay, I hope that's sufficient, but it's really, I'm not sure, maybe people who are doing machine learning as the primary activity, they would have a methodology, but I think if the simple model works, just don't try to make it complicated, because as we've seen that complicated models might lead you to overfitting, and you might find the phenomena which is not there. And don't forget that if it's a real life application of the machine learning algorithms, which can application in medicine, or I don't know, application in some other domains, you want also to be able to explain why your machine learning algorithm have taken a certain decision, and why, on which grounds, because it could be the matter of the life and death for people, or people being in jail or not being in jail, as we know that it's used, and kind of like it's already used in certain places. So from this point of view, ability, so you want to have as simple model as possible. So that's why numerical linear models with the epsilon modification of them, if your data is allowing that, is probably the first level choice. And afterwards you begin to increase the complexity of the models as it's required. And the same with the statistical methods. If you need complex statistical models, you can go for them, but one should take it a little careful. Okay, so logistic regression model family. So we want to find what is our model by optimizing the possible values of y, and we've seen that it's sigmoid if the class 1, and 1 minus sigmoid if it's class 0, or we can say it very simple. So it's 1 if the output, so this is kind of the decision point. So if output is greater or equal than 1/2, it's a class 1. If it's smaller than 1/2, it's 0. Or one can show that this is equivalent to just saying that if this beta t is greater than 0, it means that also sigmoid will be greater than 1/2. So it will be, if it's greater than 0, you are here. And if beta t is smaller than 0, you are in this class. Or you can rewrite it as essentially what you are getting. So what model family you are getting, you're essentially getting a linear models, and you need to choose beta such that if the beta t on x is greater than 0, and you need to choose such betas that you are feeding your data, so that if it's positive, you're in one class. If it's negative, you're in another class. And so we're essentially recovering linear classifiers. And in case of the multi-class classification, what do we have? We have absolutely the same game. So we have a points, and now instead of one line, which is separating one answers from the other answers, we need to draw several lines, which is separating each classes. For example, in this case, you know, if we're between these two lines, we're in the red class. If we're between these two lines, we're in the blue class. Between these two lines, we're in the black class. Okay. So, and this could be, you know, multiple problems. Yes, kind of, if it's a disease diagnosis as it's here, so that you can have several diseases which have a similar symptoms, like, you know, cold, flu, or pneumonia. So object classification, and I hope that tomorrow we'll be able to do the multi-class classification using the neural network for some prototypical examples. For example, MNIST classification will recognize handwritten digits. Yeah. So, and things like this. So over there are several classes, and it means that, you know, in some space, we can organize our points in such a way so that we can draw well-defined lines between them. Okay.
Yes, so there are two questions on Slack. I'll start with the shorter one. Is beta a hyperparameter or parameter?
Beta is a parameter.
Okay.
Beta
and then
is a
the other
parameter
one.
because it's a parameter of the model.
Okay, Mubarak, I hope you're answered. Please show a thumbs up if you're answered. And then the second one is asking about, is there need to know those equations in order to apply machine or deep learning in applied research? For example, in the field of public health or epidemiology?
You don't need to know these equations, but you need to understand these equations, because what these equations are giving you, it's giving you ability to answer for the very simple question, why? And, you know, kind of like, you know, we are saying in field of public health and epidemiology, just think for a second about, you know, COVID, yes, which we had. And you as the kind of like advisor need to tell to whatever governmental agencies that we need to go for a lockdown, which will cost South Africa, I don't know, millions or trillions of rand. Yes. And the minimum thing which they will require you at least to explain why you're giving a recommendation which will cost to the treasury so much money. So to just apply and to play around and maybe, you know, to write some even papers, maybe it's not necessary. But if you want seriously to give a recommendation to the organizations which are going to take a serious decisions, one need to be ready so that this organization will ask you a question. You are saying that we need to do X. Why we need to do it? So I think it's important to understand where it's coming from, which assumptions are built in, because you might, you know, you might understand your model might give a wonderful answer on the data which you have, and you might done everything correctly, but because your basic assumptions for the data were incorrect, you get a wrong answer for the certain classes of models. So yes, it's better to know than not to know.
So there is a follow-up question
Yes,
on the
yes. Of course they want. Okay. So now just keep in mind that let's assume that, again, hypothetically, that you give a recommendation. The recommendation is followed, and there is an unfavorable outcome, and you might be sued. And tomorrow, when there will be your defense in a court, there will be on the other side, there will be a person who is competent enough in machine learning approaches, who will be the witness of the accusers, who will ask you these questions. And who will not say, oh, no, don't tell me fairy tales about your algorithm. Why do you think that this, and this hypothesis is working? That's how these algorithms are defined. So it's a tight balance. I think it's better to know than not to know. Not only to protect others, but also to protect yourself. Okay, so I assume that we can continue without discussing politics too much. Okay, so Mubarak have follow-up question, which is beta a hyperparameter or parameter? Yes, and then how do you choose the parameter? Because to be in the fitting output, you choose this parameter by minimizing the loss function. So we have that negative log likelihood, we minimize it, and we're getting out betas. So that was, so let me just go back where it was. No, then yes, so that's how you choose a beta. Yeah, so you have your negative log likelihood function, you go through all your data, you minimize it, you get betas. Okay. Okay, so now the question is, if we have a multi-class classification, how we can choose this kind of this approach like here with the sigmoids? And the answer is very similar. So kind of we say that, you know, the probability that you are in a class K, yes, is proportional to the e to the beta x, which corresponding to that class K. And because the probability needs to be normalized, you sum up all the betas for the all possible kind of subclasses and keep your class, your given class on top. And this is called softmax. And of course, when the softmax is for the two classes, it's become a sigmoid. But in general, it's kind of, you have a vector with the numbers, and usually what is happening, you choose which number is the largest one, and that is the class which you are deciding for. And the typical example, we'll see it probably, you know, with the MNIST classification, so that we can see what is it kind of, because this is giving you the probabilities of what the algorithm thinking is the class is. So it will be, for example, it could be 0,8, 0,2. So when you just decide, okay, there is a high probability assigned to the class 0, that's why we're choosing 0, that's why we're choosing the class 0. Okay. So in the model family again, which is happening in this multi-class logistic regression, is again, we're optimizing all y's such that where this expression is going to be maximal. So kind of we need to optimize over the all y's to maximize this. So that would be the maximal, because this will be the same. So the maximum expression will be for the kind of the factor of the exponential in the numerator. Yes, so kind of the maximum of that. Okay, so we can apply the gradient descent on the negative log likelihood, and we will simultaneously update all the parameters. So again, standard game in the same way. Now, what kind of we're slowly coming to the end of this section of the lectures, and we're going now to talk about the metrics, because what we were discussing like, you know, okay, we can have a, you know, class 0 and class 1, and we're talking about accuracy. But accuracy is always the right metric? And in case of classification, it will be clear that it's not always the right metric. Yeah, because for example, yes, if we have 99, if we have what is called unbalanced data set, so if we have not the number of classes 0 and 1 are the same, so and if 99 labels are negative, so without doing anything, we can reach accuracy of the 99% by just setting f beta on x is equal to 0. But what have we learned? We haven't learned too much. And, you know, and there are some tricks, what you need to do to make a data set more balanced. But this is a situation which is very typical for the most diseases. So there are very few cases in a positive class, and the most of other people are disease-free. So, and this is the problem of the what is called imbalanced data, and there are different ways. And exactly from the field of epidemiology, there is this kind of other ways of assessing, so to say, kind of how we can approach the classification metric and what are we looking for. And as a function of the problem, you might choose this or other kind of metric of your choice. What is important for you? Is just an accuracy is important or something else? And the first one will deal with something just called true positive, true negative, false positive, and the false negatives. And so what is a true positive? So it's what is actually positive, and it's predicted by the algorithm as positive. True negative is what is actually negative, yes? So kind of class 0 and predicted class 0. Class 1 and predicted class 1, for example, yeah? And false negative is they are actually positive, but predicted negative. And false positive are actually negative, but predicted positive. And the typical, or kind of, the accuracy is true positive plus true negative divided by the total number of inputs. Error is 1 minus accuracy, yes? False positive plus false negative divided. So just kind of like things which are get right, yes, what is accuracy? True positive plus true negative, yes? Actually positive, predicted positive. Actually negative, predicted negative. So you count all of those cases and divide it by the total number of data points. Error is 1 minus that. But that, as I mentioned, might be not enough just because of the nature of the problems. Sometimes, you know, you're dealing with unbalanced data sets. And in this case, very often people introduce a notion which is called confusion matrix, where they put the following kind of table like this. Yes, so predicted class, actual class, and your true positive sitting here, yes, actual yes, and predicted yes, or actual 1 and predicted 1, actual no, true negative, and predicted no, so actual 0 and predicted 0, false negative, so actual yes, but predicted no, and actual false positives, actual no, but predicted yes. And as I mentioned, as a function of the problem, this might be a better way of looking on things, and there is some derivatives, or there are some derivatives of these numbers. Yeah, for example, you know, we can just cook up some, you know, in some problem, we have the following, you know, matrix. We have 3 true positives, 37 true negatives, 4 false negatives, and 6 false positives. So accuracy is 80%. Yeah. Okay. So, but sometimes we have this imbalance, kind of, for example, for the disease control and things like this. Sometimes what you want that you don't have a false negatives or false positives. Yes, so kind of like stop. Sometimes, so no, so you don't want the false negative. So you don't want that you have an actual yes, but it predicted no. So you want to minimize this. And if by doing that, this number is increasing, it's maybe not that bad. For example, for the disease detection, because, okay, if some people will have to suffer a little bit more because, you know, they've been false positives, okay, they can do an extra test and be free to go. But we definitely don't want with certain diseases, we don't want to let people with that diseases kind of go untreated. Yes, kind of like, and this just give you a little bit more fine way of measuring. Yeah. So, and there is 2 standard terms which I use. One is the sensitivity, and another is specificity. And again, in medical literature, which is dealing with the tests, it's kind of very common term. So sensitivity is what fraction of actual positives are predicted positives. Okay, so kind of like this is an important thing. Yes, kind of what fraction of the actual positives are predicted positives. Yeah. So good sensitivity. So if you have a disease, the test correctly detects it. It's also called true positive rate. And specificity is what fraction of actual negatives are predicted negative. So good specificity. So if you don't have a disease, that the test says so. Yeah. And it's also called true negative rate. And it's really commonly used in medicine or in epidemiology. Yes, so kind of like, and sensitivity is these 2 numbers, you play with these 2 numbers, so kind of like actual positives, so ratio of the true positive on true positive plus false negatives. Yes, so this is sensitivity. So, and this is specificity. Yes, so kind of like, and on the good tests, including the COVID tests, kind of like, because, you know, those tests are available, not only the COVID test. On the good test, they indicate these 2 numbers. What is the sensitivity and what is the specificity of the test? And also, for diseases like COVID, it's also depends on the on how many days after the infection, for example, because that's also is an important parameter. Okay. So, and in that examples which we have, kind of like we can calculate what was the sensitivity of the classifier and what was the specificity. And the sensitivity is obviously from here, and one can guess it, yes, is not too good. Yes, kind of sensitivity is quite low, below 50%. Yes, because for the total 7 examples, in this confusion matrix, we get 3 real positives and 4 false negatives. So that one which is supposed to be positive, but was misclassified by the classifier. And the specificity looks quite good. And remember that the accuracy of this for this confusion table was 80%. And one would think that, oh, it's quite a good test. But in fact, it's not so good when you begin to look a little bit more kind of fine for the numbers. Okay, so that was sensitivity / specificity. So there is one more possible, but there are many more. But I mean, this is just an examples of the of this measures of the not accuracy, but of the predictionability. Yeah. So, and another 2 couples of it's a precision and recall. So recall is what fraction of the actual positives are predicted positive. So good recall, it's essentially, this is just a sensitivity. Yes, kind of it's the same thing. So if you have a disease, the test correctly detects that you have it. Yeah. And the precision is what fraction of predicted positives are actual positive. So good precision, if test says you have a disease, then you have it. So also called positive predictive value. Okay. And how it's calculated from the confusion matrix, it's calculated like this. So recall is essentially the same as the sensitivity, but because it just coming from the different subfield, it's called recall and not sensitivity. And the precision is, so you have predicted yes, but out of those predicted yeses, there will be a true positives and the false positives. And what you wanted to see is you want to see what is the fraction of the true positive out of all positive predicted. So this is called precision. So kind of like you have 2 couples of the parameters to check whether your prediction kind of to check your kind of classification accuracy. Yes, sensitivity, specificity, or precision recall. And as a function of the problem or as a function of the field, you might need to calculate this or other one. And in our example, 3, 4, 6, 37, we can again, and you should hear it's even more radical. So we get, yes, recall as a sensitivity is the same, quite poor, but also precision is quite poor, yes, because for the all of 9 cases which are predicted yes, only 3 are the real ones. And the 6 or majority are the, so to say, the error ones. Okay, and I think that would be it what I have for you for today from the lecture perspective. And is there any questions? Because in the afternoon, we're going to go through a few notebooks, and I was asked to give some examples, and over there, we're going to have some examples, and also there will be some space to play with the parameters so that I can keep you occupied for the rest of today. And for tomorrow, what I'm planning for tomorrow, because we now went for the very basic approaches, and tomorrow we're going to talk a little bit about what is called, because now our methods have a parameters, and it's called the parametric methods, so those betas. And tomorrow we're going to talk a little bit about non-parametric methods, which are relevant for the unsupervised learning. And we're going, of course, to talk about, because now we have 2 days, about the neural networks and some application of the neural networks. Okay. Is there perhaps another resource which discusses the equations as maths and stats skills are very lacking? There are zillions of resources where the where the where we can you can learn the it's also depends, like, you know, what kind of kind of math skills are you talking about? If you're talking about the math skills for the machine learning per se, there are courses. I mean, you just type in the YouTube mathematics for machine learning, and you will get a lecture courses where the people are talking about, because for the machine learning, mathematics more or less is boiling down to the linear algebra plus for the and a little bit of calculus. For the statistics, you know, if you want to do things related to the statistic theory of learning or kind of statistical approaches, it's a little bit more difficult. But in that case, you just need to go to the courses on statistics, on mathematical statistics. And on Wednesday, you're going to have a full day of the probability theory and statistics. And the lecturers from Wednesday will be much more qualified to tell you what are the good courses. But again, it's like you just go on the YouTube, there will be several courses, and you choose the lecturer by the, you know, is that like, do you like how the person is talking? Do you like how the person is explaining? Because, you know, I might like one lecturer and you might hate him or her, and or kind of it doesn't gel for whatever reason, but some other person who might find boring or too fast or whatever is good for you. So kind of like it's what is definitely not lacking nowadays in the resources for that. You know, there is more than enough online. You just YouTube and Google, and many universities after kind of, and from this point of view, COVID was very blessing, because all the universities, including UKZN, were forced to do online learning. And now on the YouTube, there are humongous amount of courses which also have, you know, corresponding courses, kind of lecture notes on the websites of universities. Because, you know, again, I'm utilizing the lecture notes of University of Pennsylvania. You know, there are many other universities which put their lecture notes online. There is open courseware from MIT. So it's like, there is really no restriction. It's much easier than it was 10 years ago. Okay, so I just can't wait for the application of all that. Okay, yes, it's coming. Any reference book to assist to learn the material in your slides you recommend? I don't know. Again, it's like you just grab any book and let me, I don't know, kind of like also there are many books. I cannot even recommend one, because, like, you know, there's so many, and kind of like, you know, if you just want and so I'm using the lecture notes from this University of Pennsylvania. So, and they have a resources page, you know, for the course, and they have, you know, a long list of books, video lectures, and things like this. So it's really, it depends like what kind of lecture notes you want and what for. If you want it for basic machine learning, or if you want it for some advanced chapters, if you want the books on the deep learning. For the deep learning, the best book is probably to start with will be the book by Benjo Goodfellow, Deep Learning, which is available for free as a website. It's www.deeplearningbook.org, and it's like it's really, there is more than enough places to learn machine learning without any issues. So that's what I want to say. It's just your ability to do it every day for some time. Any other questions? Yes, and I see that, yes, also Benjamin answered to this question about knowledge of equations. Yes, Python have it all built in, but the Python will never tell you why. So, if you just want to write a paper in epidemiology, maybe Python will just help you out of the box. But if you need to give an advice which requires justification, one need to know the equations and the basis for the equations.